We have spent the last several meetings talking about hypothesis testing, and we're going to continue to talk about hypothesis testing today. We've talked of it thus far in very simple terms, comparing one group performance with another group performance. And we've done that in two ways. First of all, by conducting a z-test, and then more recently by conducting a t-test. The decision to use a z-test or a t-test is a function of sample size. When sample size is small, that is less than 100, the rule is that you use a t-test. When sample size is large, greater than 100 or more, then you use a z-test. Whether you're using a z-test or a t-test, the process of hypothesis testing has been the same. We have computed, or we have defined a critical value of the test statistic, and then computed an observed or obtained value of that test statistic, and used those two pieces of information to evaluate the null hypothesis. And I think we've been through that routine sufficiently often that it's familiar now to all of you. When you're conducting a t-test, or whether you're conducting a t-test or a z-test, you compute the obtained or observed value of the test statistic in exactly the same way. That is, by invoking exactly the same formula. X bar 1 minus X bar 2 divided by the square root of, and so on. In order to determine a critical value of the test statistic, in the context of z-testing, you need to know two pieces of information. You need to know the research hypothesis so that you can determine whether the test should be one or two-tailed. And you need to know the level of alpha. When you're conducting a t-test, you need to know those same two pieces of information, but you need to know a third piece of information, and that is the degrees of freedom. And the degrees of freedom are given by, generally, uppercase N minus K, where K is the number of groups, and uppercase N is the total number of people in the sample. It's also given by lowercase n1 plus lowercase n2 minus 2. However you compute those degrees of freedom is incidental. Are there any questions about either z-tests or t-tests, or when you would use one as opposed to the other? Hearing none, we march on. Today what we're going to start looking at is analysis of variance. Analysis of variance is more commonly referenced as ANOVA. Two general observations at the outset. The first is that we are going to depart at this point from computation. What we're going to focus on is interpretation of ANOVA output. An analysis of variance uses an F statistic. And we could do precisely what we've done in the other two situations, and that is define a critical level of F, compute an obtained value of F, and then compare the two. If you have looked through the text, you will have discovered that that is a tedious process, much more arithmetically complicated than the two previous situations. And we're going to forego all the math. What we're going to focus on instead is, at the front end, deciding whether the test is one or two-tailed, and the level of alpha and so on, and at the back end, interpreting analysis of variance output. So my first general observation is that we're going to move away from computation and focus much more exclusively on interpretation. The second observation I have is that analysis of variance can take a huge number of forms. When we began our discussion of t-testing, I indicated to you that there were two kinds of t-testing: an uncorrelated t-test and a correlated t-test. And I indicated to you that there were two circumstances under which a correlated t-test was the appropriate version of t-testing to use. One of those was where the same subjects appeared in both groups. For example, the same subjects evaluated both candy bars. And the other was a situation in which you matched people on some critical variable. For example, their general liking for candy. And then assigned one of the pair to evaluate candy bar A and the other to evaluate candy bar B. This sort of research is common if any of you are in communication disorders, but it's also common in medical research in general, where persons are matched on some critical variable and then one receives a treatment that the other does not. We didn't look at either of those two circumstances in any detail whatsoever. We focused on uncorrelated t-testing, a situation in which persons are randomly assigned to either group 1 or group 2, so that the responses of persons in group 1 is independent of or uncorrelated with the responses of persons in group 2. Analysis of variance can take a comparatively huge number of forms. We're going to look at the simplest of those forms, and that is a completely randomized ANOVA with a single independent variable. What that means is, first of all, the notion of completely randomized. Let us assume that there are 3 levels of an independent variable. We could have 3 candy bars. Persons are randomly assigned to one group or the other. This is nothing more than an extension of uncorrelated t-testing. Z-tests and t-tests are useful when you're comparing one group with one other group. As soon as you move away from one group versus another group, you're into the world, and you're testing for between group differences, you're into the world of ANOVA. We could have a 4th and a 5th and so on levels of this independent variable, and a completely randomized design is still one in which persons are randomly assigned to one group or the other. For example, in medical research, we could be testing the effects of a particular medication, and we could have 0, 5, 10, 15, and 20 milligrams of the medicine per day. If we assign participants in the study randomly to one and only one of those groups, then the appropriate form of analysis of variance is a completely randomized ANOVA. The second observation I made was that we're only going to look at an instance in which there's a single independent variable and a single dependent variable. That is the simplest form of hypothesis testing, in which we're testing the researcher's notion that changes in A cause changes in B. Changes in the amount of violent television programming that children watch causes a change in their level of aggression. That would be an example of the sort of hypothesis that will be tested using the version of ANOVA that we're going to look at. So we will have a design in which there are multiple levels of B. B1, B2, B3, B4, and so on. And we will have scores of individuals within those groups. And we will then have a series of independent means, X bar 1, X bar 2, X bar 3, and X bar 4. You understand that very easily we could distinguish between males and females in this design. We would then have two independent variables. The design would be a 2 by 4. The 4 levels of B and the 2 levels of A, which would be gender. This too would be a completely randomized design, but it would include 2 independent variables and a single dependent variable. In this design, the one that we're going to focus on, the argument, you understand, is simply that changes in A cause changes in B. The argument in the second design is that 2 factors, A and B, predict some outcome variable or dependent variable, let's say C. So in this design, this 2-factor design, you have effects that are due to A, gender, you have effects that are due to B, dose size, and then you have an interaction effect. The interaction effect between A and B. In this design, we have only effects due to A. Yes? Are there any questions at this point about analysis of variance in general? Yes.
So the changes in B is correlated with A?
A and B are seen as 2 independent explanatory variables, or 2 independent variables, two predictor variables. And we still have a single dependent variable. We might be measuring blood pressure of each person in this study. Yes? Clearly, research becomes much more complicated than that. Researchers want to know not simply the effect of perhaps the medication on blood pressure, but on body weight or on levels of depression. Antidepressants, for example, the effects of antidepressants. That is, they're interested in multiple outcomes. This may bother you, but this is an example. If you have multiple dependent variables, you simply have what is called multivariate analysis of variance. And you have tests for the effects of the independent variable or independent variables on each of the dependent variables. And you would interpret those separate from one another. So you're back to looking at one dependent variable and the effects of one or more independent variables and their interaction. I'm not seeking to confuse you by building upon this basic building block in which there is a single independent variable. I'm doing two things. One is anticipating an issue that we will look at in this discussion. That is this notion of this interaction effect. And second, trying to indicate to you how easy it is to start building upon this basic design. We could add a third variable, a third independent variable, a fourth independent variable. We could assign subjects to groups in a different way. If you encounter those sorts of more complex designs, you shouldn't throw down the journal or the research and say, I just can't understand this. Because in the end, whether there's one or more independent variables and one or more dependent variables, ultimately the research is headed back to this design. And as we shall see, ultimately to comparing one group with one other group. That is ultimately, in this case, comparing B1 to the other levels of B, B2 to the other levels of B, and so forth. We're headed back to, no matter where you start from, you're headed back to, does one group differ from one other group? Are there any questions? Let's then take an example. Let's assume that we have distinguished between, we have one independent variable, and the independent variable is level of television viewing. And we have one dependent variable, and that is level of aggression. So our argument is that the researcher is predicting that changes in TV viewing, amount of TV viewing, cause changes in aggression, displayed aggression. let's too assume that we've distinguished between 4 levels of television viewing. That is, we have 4 levels of the independent variable I. And we somehow measure aggression. The initial way of measuring aggression, as I'm sure many or all of you know, was by the classic initial form of this study was that children would be sat down in front of a television. They would watch TV content that lasted for 10 minutes or 15 minutes or 30 minutes, and that content would differ systematically in the amount of violence that was involved, that was depicted. Each child would then be placed in a room with a Bobo doll, one of those dolls that you hit, it bounces back up and you can hit it again. Yeah. And the researcher would simply count the number of times the child hit the Bobo doll. Whether that's a good operationalization of aggression or not, let's put that aside for the moment. Let's assume that in this sort of classic way, that's how the researcher has measured aggression in each of the children, is to count the number of times that the child subsequently hits a Bobo doll over a 3-minute period. Let's assume that persons in group A, respectively, hit the Bobo doll 3 times, 6 times, 3 times, 3 times, once, twice, and twice. So that the mean of group 1, X bar 1, equals 2.5. Let's assume that persons in the second group, that is children who watched television content that included a systematically higher level of violence, hit the Bobo doll 4 times, 4 times, 5 times, 4 times, 3 times, twice, 3 times, 4 times, and 3 times. So that the average number of times that the children in group 2 hit the Bobo doll was 3.5. Persons in group 3, 7, 8, 7, 6, 5, 6, 5, and 6. And the mean of group 3 then is 6.25. And children who watch the content with the highest level of violence hit the Bobo doll 7 times, 8 times, 9 times, 8 times, 10 times, 10 times, 9 times, and 11 times. So the mean score for that group was 9.0. What analysis of variance does is to take all the variance in these observed scores and in this instance divide it into 2 types. If we imagine that this represents all of the variance in these individual scores, analysis of variance partitions that variance into within group variance and between group variance. It partitions the variance into 2 types, within group variance and between group variance. Let me ask you this. can you explain the between group variance? That is, can you explain the difference between 2.5, 3.5, 6.25 and 9.0? What is your explanation for those differences, the differences between groups? Yes.
The higher level of TV viewing causes aggression.
Yeah.
Regression.
The explanation for these between group differences is the individual, the groups watched television content containing different levels of depicted violence. That is, you can explain the between group variance as a function of the independent variable or treatment variable. Can you explain the within group variance? Can you explain, for example, why one child in group 1 hit the Bobo doll 6 times, and another hit the Bobo doll once, and another hit the Bobo doll twice, and so on? You cannot explain within group variance because it's not obviously a function of the dependent variable. It's a function of some other variable. So that in analysis of variance, within group variance is unexplained variance, and between group variance is explained variance. Are there any questions to this point? Yes.
So why is between explained?
We can explain the difference between, and the question is, why is between group variance explained variance? We can explain the difference between the average of these 4 groups by appealing to the independent variable. That is, the difference between the groups is a function of their exposure to television content that included systematically differing levels of violence. What you cannot explain is the variance that occurs within the groups. After all, everybody in group 1 watched the same television content. So why did one of the children hit the Bobo doll 6 times and another hit the Bobo doll only once? Certainly not because, by definition, not because they watched different content. So within group variance then is unexplained variance or error variance. Are there any other questions? At this point, what we could do is use these scores, and there are examples of this in the text. We could use these individual scores to perform an analysis of variance by, again, going to an F table with the relevant information and determining a critical value, a critical level of F, by then using these observed scores to compute an observed value of F, and then comparing those scores to interpret the null hypothesis. Mercifully, we're not going to do that. What we're going to do is we're going to presume that we or somebody else has entered these data appropriately into a computer, pressed analysis of variance, and we got output. Now it's making, the difficulty now is making sense of that output. First of all, the output will look like this. There will be one term called between group. There will be a second within group. This is the source of the variance. The source of the variance. God, this is getting worse. I would give $1,000 for a computer that was left-handed. The first column then is the source of the variance. The second column is the sums of squares, simply marked SS. Sums of squares is simply represented as SS. And in this instance, the between group sums of squares is 194.5, and the within group sums of squares is 41.0. So that the total sums of squares is 235.5. The next column will be headed DF, and you should already know what that indicates. Degrees of freedom. Degrees of freedom. How many groups were there? 4. There are then, if K is the number of groups, there are K minus 1 degrees of freedom associated with the between group term. That is 4 minus 1, that is 3. And in general, there are N minus K degrees of freedom associated with the within group term, which in this case is 28. And the total number of degrees of freedom is 31, which is N minus 1. There were 32 people in the study. There were 8 people in each group. And I indicate this to you because I want to emphasize that there's nothing new about this. There is really nothing strange about it. There are things that are new. There's nothing strange about it. The next column is headed MS. MS means mean square. MS. MS, mean square, is nothing more than the sums of squares divided by the associated degrees of freedom. So that the mean square associated with the between group term is 194.5 divided by 3, which is 64.833. And the mean square associated with the within group term is 41 divided by 28, which is 1.464. The final column, well, not the final column. The next column is headed F. This is the obtained value of F. This is the equivalent to the obtained value of T or the obtained value of Z. In order to determine F, F equals the mean square of the between group term divided by the mean square of the within group term. That is, in this case, it's 64.833 divided by 1.464, which is 44.28. The final column is P. And P in this instance, I'm making this part of it up. But let's assume that P in this instance is 0.007. Let me ask you, if we reject the null hypothesis, what would we conclude?
That the level of watching TV doesn't affect, that it does affect the level of aggression.
If the null hypothesis is that x bar 1 equals x bar 2 equals x bar 3 equals x bar 4. That's the null hypothesis. Stated in a different way, the null hypothesis is that exposure to differing levels of violent content does not affect subsequent observed aggression. If we reject that statement, would you agree we would conclude that changes in the amount of violent television content causes changes in child viewers' subsequent aggression? Yeah? Let's assume that we've established alpha equal to 0.01. That is, we're willing to take a 1 in 100 chance of committing a type 1 error. Yes?
On the mean square, what do we divide the sum of squares by? I couldn't read your little symbol that you wrote.
Do you mean, how do you get F? Or how do you get the mean square? To get the mean square, you simply divide the sums of squares by the degrees of freedom, by the associated degrees of freedom. So for the between group term, that is, you divide 194.5 by 3, which is 64.833. And the within group term, you divide 41 by 28, which is 1.464. Then in order to compute F, you simply divide the mean square for the between group term, 64.833, by the mean square for the within group or error term, which is 1.464. And if you do that, the resulting F's value is 44.28. Are there any other questions? So my question is, what would you do? What would you do with the null hypothesis? Would you reject the null hypothesis and conclude that differing amounts of exposure to violent content or exposure to differing levels of violent content produce differences in subsequent aggressive behavior? Or would you conclude that there is no such effect? That is, would you reject the null hypothesis, or would you fail to reject the null hypothesis? All those who say you would reject the null hypothesis. One brave soul, why would you reject the null hypothesis?
Because it's lower than 1. It's lower than 1%.
So what's lower than 1%?
It's lower than 1%, that you could be wrong. Error or whatever.
What is the likelihood of committing a type 1 error if you reject the null hypothesis?
100%.
Or 7,000? Or it's 0.007. Let's not get into, yeah. The likelihood, probability of committing a type 1 error, which is the only error that you can commit if you reject the null hypothesis. The likelihood of committing a type 1 error in this instance, if you reject the null hypothesis, is 0.007. That's what this p-value stands for. That's the information that the p-value provides. It tells you the likelihood of committing a type 1 error if you reject the null hypothesis. Yes.
But wouldn't you fail to reject if you do the little bell-shaped curve? You wouldn't, because
we're out of the bell-shaped curve.
Well, I mean, I'm just saying. You know how you showed us how to.
Well, we're not out of the bell-shaped curve.
Well, you know how you showed us we draw it, and then you make the little line. If it falls underneath it, then you'll fail to reject. Or if it falls in that little shady region, then you'll do reject. But wouldn't that 0.007 not fall in the shady region? Draw it on the thing.
I've been struck dumb. We are still dealing with a sampling distribution of sample mean differences. But in this instance, the number of sample means is greater than 2. But nonetheless, we're still dealing, as you've indicated or surmised, with this supposedly, what I've tried to present here as a bell-shaped curve. That's pathetic. Nouveau art. What can I say? We've tested null hypotheses in the past, in z-testing and in t-testing, by determining the value, that is, how many standard deviations you have to depart from the center of the distribution, which is marked by x bar 1 minus x bar 2 equals 0. And then using that as a boundary marker. And in the two-tailed test, we would have 2 domains, one at the positive end of the distribution and one at the negative end of the distribution, that we would be required to test. We've then taken an obtained or observed value of the test statistic and we've placed it in this distribution. saying that if it is in one or other of these shaded regions, then we would reject the null hypothesis, yes? And if it's in this striped region, we would fail to reject the null hypothesis. We're not doing that anymore. We're shortcutting that process. And rather than you comparing a critical value of some test statistic with some obtained value of the test statistic, we're comparing alpha with p, where alpha replaces the critical value of the test statistic and p replaces the obtained value of the test statistic. In this instance, then, we have set alpha to 0.01. That indicates that we are willing to take a 1 in 100 chance of committing a type 1 error. I need more space. We are willing to take a 1 in 100 chance of committing a type 1 error. If we go back to that 2 by 2, where the researcher can either reject the null hypothesis or fail to reject the null hypothesis, the null hypothesis is true or the null hypothesis is false, right? We're interested only in this portion of that 2 by 2. We're not interested in this portion. Because our rule is that you would agree that if you reject a true null hypothesis, you've committed a type 1 error. Yes? Yeah? Our decision rule, when we set alpha equal to 0.01, is that it says, in order to reject the null hypothesis, I must be at least 99% sure that it is false. That is, I'm willing to take a 1% chance of committing a type 1 error. Would you agree? That's the decision rule that you've established in setting alpha equal to 0.01. What is the probability of, given these data, of committing a type 1 error if you reject the null hypothesis? We've already been given the answer to this. What is the probability of committing it? In this case, with these data, what is the probability of committing a type 1 error if you reject the null hypothesis? 0.007. That's the information, that's what P is. It's probability of committing a type 1 error. You're being asked to take a 7 in 1,000 chance of committing a type 1 error. You're asked to take a 0.7% chance of committing a type 1 error. You were willing to take a 1% chance. So is the likelihood of committing a type 1 error greater or less than your willingness to commit a type 1 error? It's less than your willingness to commit a type 1 error, which was 1%. The likelihood then of you committing a type 1 error if you reject the null hypothesis is greater than 99%. You therefore reject the null hypothesis. I mean, I hope you come to understand this, but the mechanical rule is if P is less than alpha, you reject the null hypothesis. If P is greater than alpha, you fail to reject the null hypothesis. And in this instance, P is less than alpha. Are there any questions? Yes.
Is this considered one-way ANOVA or two-way? What we're doing?
This is one-way ANOVA.
Okay, because I entered in all the numbers in the calculator, and I got different numbers. Is that just a mechanical error, or I mean, because I got the same degrees of freedom and everything else?
I don't know. I don't know. I mean, it could be because the example I'm using that the author has miscalculated. It could be because you've miscalculated. It doesn't matter. You won't be called upon to compute sums of squares or mean square. You might be asked what are the appropriate degrees of freedom or something of that kind. But you will not have to compute an obtained value of f. You will not be required to use an f table and decide upon a critical value of f. We're departing from that process. And instead, what I'm trying to do is to get you to understand what appears if you do this on a computer. This is the output that you will see. Now, how do you make how do you evaluate the null hypothesis? You look at the p-value. Yes.
I'm having confusion on how to actually find the p. I think I understood everything up until that point.
Okay. Okay. First of all, let me get out of my head something that I need to get to. Very minor issue. If you were to see this reported in a journal, it would be reported in this way. F with 3 and 28 degrees of freedom equals 44.28. P less than 0.01. That is, it would provide you the degrees of freedom, the author would provide you the degrees of freedom, the observed value of F, and the probability of committing a type 1 error. To get back to now to try and answer your question. How to compute P? The simple answer is you don't. It's just given to you. What the computer has done is to go to a table of F values and located 44.28 when with 3 and 28 degrees of freedom. And then it's looked for area beyond F. And the area beyond F is 0.007 of all of the scores. That is, had we gone about this as we've done previously in the context of z-testing and t-testing, the obtained value of F would be way down here. And we would discover that the proportion of all scores beyond an F of 44.28 with 3 and 28 degrees of freedom, or the area under the curve would be 0.007. You won't be called upon to do that. But your question is useful because you should see, or I should be able to demonstrate to you, that really we're not doing anything different here. We're just looking at it from the other direction. We're letting a computer do the work for us. In a z-test, a two-tailed z-test, would you agree that if we had set alpha equal to 0.05, we would have markers of plus and minus 1.96, yes? And that 0.025 of all scores would be beyond this marker, and 0.025 of all scores beyond this marker. So that if an observed score fell in this range, the likelihood of committing a type 1 error would be something less than 0.025. That is, the p-value would be something less than 0.025. P is the proportion of scores beyond that specific F value, or the area under the curve beyond that specific F value. But more importantly, P is the probability of committing a type 1 error if you reject the null hypothesis. Are there any other questions? Yes.
With the degrees of freedom, you got 31.
Yeah, the total degrees of freedom are 31.
Isn't it n minus 1, or did I do something wrong with the 28?
There are there's 32 people in the study. There were 8 scores in each group, and there were 4 groups. So there were 32 people in the study. So that, you remember when I first introduced the notion of degrees of freedom, I tried to explain it in a sense what degrees of freedom were by indicating to you it's a number of scores free to vary if you knew the mean. And we discovered that in a group of 3 scores, 2 were free to vary if you knew the mean. That is, if I tell you 2 scores and the mean, you know the third score must be of a particular value. In general, the number of scores that are free to vary then is the number is n minus 1. So that, and all I'm indicating to you here is, we're back to that n minus 1.
Well, I just thought 28 plus 3 was 31.
It is.
And then you plus minus 1, right?
You're then at n minus 1.
And then it'd be 30.
No, it would be 31, because there are 32 people in the study. 4 8s are 32. There are 8 people. There were 8 scores in each group. That represents 8 people. Yeah, we're good to go. Okay, we're good to go. But we ain't finished. Yes.
So we're pretty much just be responsible for being able to identify.
Let's not go there.
Okay. Yeah.
Let's not go there. Let's not deal with exams at the moment. Let's just get lost in the fog here and enjoy it. Okay? We have rejected this statement. X bar 1 equals X bar 2 equals X bar 3. Oh, God. equals x bar 3 equals x bar 4. Yes? We've rejected that statement. That's the null hypothesis. X bar 1 was 2.5. X bar 2 was 3.5. X bar 3 was 6.25. And X bar 4 was 9.0. Why have we rejected this null hypothesis? Did we reject it because X bar 1 doesn't equal X bar 2? Did we reject it because X bar 1 doesn't equal X bar 3? Did we reject it because X bar 3 doesn't equal X bar 4? Did we reject it because X bar 1 and X bar 2 don't equal X bar 3? The answer to this question is, I don't know. I don't know. And that's all I have to say. No, before you go, I clearly do have something to say. If I didn't, it would be money back time. You know, he's only told us part of the story. You know, I tell you, in the end, the big bad wolf gets its way. I'm always pulling for the big bad wolf, and I know at the end somebody's going to shoot the head off the big bad wolf. We will talk next time, we will discover next time how you go about determining specifically why you've rejected the null hypothesis. That is, specifically which groups differ from which other groups. I'll see you next time.